welcome back to our computer architecture lessons. Today we continue with the memory hierarchy design. So, the last time we have seen the stack of computer architecture where we had the hardware and devices on the bottom and logic gates and circuits, and then we started the software with the operating system, which contains the device drivers as well as manages the resources by giving slices of CPU time and parts of the memory to the processes or instances of running applications. We have seen the machine level language or the processor instruction set, and we have also seen the higher level language and then the applications on the top. One of the resources that the operating system would manage is the memory, the RAM or random access memory, as well as the registers, that is the much faster memory inside of the CPU, inside the processor, cache that can be within the next to the registers in the CPU, as well as disk storage, that is hard drives and removable drives and other storage tapes and other storage media. So in that sense, we have an entire hierarchy of memories, and the true reason we have all these hierarchies is because of their cost or their expense. The bigger they are, the slower they are, and the cheaper they are, which means that the hard drives would be cheaper and slower than the main memory or the RAM, which will be cheaper and slower than the cache inside the CPU, which will be cheaper and slower than the registers inside the CPU. As we can see here, the registers are on the top of the pyramid. That is the fastest memory that we can have available, that is directly accessed by the CPU, and it is within the CPU, and that is why it is faster and easier to access. All these other memories, like the main memory and the disk, are farther than or are separate from the CPU, and from the point of view of CPU, accessing those takes a long time, as we have to go out on a bus to reach those external memories. So once again, the true reason for this is the cost, because the bigger and slower they are, the more cheap they are, and that allows us to have more storage at a reasonable expense. From point of view of the CPU would want all of the memory to consist in registers. Human beings would want the same thing, as this would speed up the computer tremendously. However, it will be very, very expensive. That is why it is not practical, and it is not currently done in this way. So let's have our introduction. Programmers want a limited amount of memory, like with low latency. This means that it's quick and easy to access. So the fast memory technology, however, would be more expensive, as we just mentioned, and that is the reason why we have all those memory hierarchies. So we're going to organize the memory system into a hierarchy to bring up a more optimal balance or level in between the speed and cost of these memories. By placing the memory into such hierarchy, we could create what is called a virtual memory, to where the difference or the communication from registers to cache to RAM to disk would be seamless, or it will look like it is all one memory space. Temporal and spatial locality ensures that nearly all references can be found in smaller memories, and that gives the illusion of large fast memory being presented to the processor. So let's see some illustrations of these memories, of the memory hierarchy. As we mentioned, the fastest and the best available memory that we have are the registers that are sitting inside the CPU. The reason they're fast is because they are inside of the CPU. So the CPU, or processor, central processing unit, can easily access those memories at a high speed, as it does not need to go outside of itself onto a bus to look for the memories. Level 1 cache will be the next closest to registers in terms of speed and cost. Then we have level 2 cache and level 3 cache, and the reason we have all these levels is, again, the cost and the speed. The slower they are, the cheaper they are, and the larger amount of them we can afford to place into our system. Then we would go, if outside of these caches, we would go onto the memory bus to access the main memory, which is faster and smaller than the disk storage. Once again, we would need to go onto another bus, an I/O bus in this case, to access the hard drive or the disk storage. You can see the example sizes here underneath of each of those memories, and we can see how their size changes as we go up and down the hierarchy. As we go up and down the hierarchy, we notice the size and the speed changes, as well as the cost. So the registers would be the smallest, 1000 bytes, but they will be the fastest. Level 1, level 2, level 3 cache, as you can see, progressively the size increases, as well as the time for access increases. Level 1 cache would be of size 64 kilobyte, while level 3 would be 2 to 4 megabytes. Main memory would be 4 gigabytes up to 16 gigabytes. And there is a huge difference in the access time. Level 1 cache can be accessed in 1 nanosecond, while the main memory in 50 to 100 nanoseconds. From point of view of the CPU, that's a very long time. Next, we have the disk storage. We can see much bigger sizes from 4 terabytes to 16 terabytes. However, the add time to access disk is from 5 to 10 milliseconds. Here we're talking nanoseconds and we're talking milliseconds. So these numbers are given for a server machine. For a mobile device or for a personal computer, the sizes of the memories will be smaller. As we have seen in our first lecture, we human beings, as well as scientists and developers and entrepreneurs, we are constantly looking for new technologies that will be better improved with increased performance in comparison to the previous technologies. So we can see how the development of CPUs and memories proceeds through time in this visualization, and how is the performance affected by these new technologies. As the time passes back from 1980, 85, 90, 95, 2000, we can see upwards trend for the CPU design and processing time. Again, we see an upward trend for memory processing time and sizes. However, the memory is growing in a much slower rate, the memory development efforts, than the CPU development efforts. So that is what we know. What we notice here. So memory hierarchy design becomes more crucial with recent multi-core processors. We have explained in our lecture last time that the CPU really can only do one thing at a time, and if it is to run any more than one application, then those applications would need to have the CPU or processor time divided in between them, and each one of them given a small slice in time to run. Now, if we have multiple cores for our CPU, we could give one application to one core and the other application to the other core, run them both in parallel, and this way finish much quicker or have a much more performance efficient applications. So let's look at aggregate peak bandwidth that would grow with the number of cores. Intel Core i7 can generate 2 references per core per clock. If we have 4 cores, and 3.2 gigahertz clock, we would end up with 25.6 billion data references per second if we are using a 64-bit computer. And with 12.8 billion as 128-bit instruction references. So the RAM, the random access memory bandwidth is only 6% of this. Okay, so let's continue now with the Okay, so let's move on to the next subject, performance and power. The high-end microprocessors would have greater than 10 megabytes of cache. Cache inside the CPU, this means on the chip. It will consume large amount of area and power budget. Let's look at the memory hierarchy basics. What happens if we are looking for parts of an instruction that we will call a word here? That would be the smallest unit of memory that we can manipulate on this machine. So if it is a 32-bit machine, the word would be 32 bits. If it's a 64-bit machine, the word would be 64 bits. If we are looking for a piece of memory or parts of the instruction or parts of the data of the application that it needs to run, and if we're not finding it, a miss would occur. So if the miss occurs, we would fetch from lower level hierarchy, recording higher latency for references. Lower level may be another cache or the main memory. Also, we would fetch the other words contained within the block. Okay, we will also fetch the other words contained within the block and will take advantage of the spatial locality. We would place the block into the cache in any location within its set, which is determined by the address. Okay, so memory hierarchy basics. We have a direct map cache, or one block per set, and then we have fully associative cache, which means that we only have one set. Writing to the cache has two strategies: write through, which means immediately upon lower levels of hierarchy. Write back, we would only update the lower levels of the hierarchy when an updated block is replaced. Both strategies would use a write buffer to make writes asynchronous. What does it mean, a miss rate? So we mentioned here, if we're looking for a word and it is not found into the cache, a miss would occur. Causes of misses: what would cause such a miss? Alright, so compulsory first reference to a block, capacity, blocks discarded and later retrieved, that could cause us to lose the information that was in there. If we were updating our code and the book was published during that time, it means that you were late. Program makes related references to multiple addresses from different blocks that would map to the same location. If they're mapping to the same location, that would be a conflict. The misses and the miss rate times the successfully accessed rate would give us, divided by the instruction count, would give us the ratio of the hit and miss ratio. We mentioned that cache is added as one of the fastest memories available because it is inside the CPU. So we could, in addition to having the cache to increase our speed and performance, we could do some cache optimizations to improve our performance even further. We could use a larger block size. So remember, a word is the smallest block size. So if the computer is 32-bit computer, the word will be 32 bits. If it is 64-bit computer, the word will be a 64-bit. So this formula would allow us to compute what is the miss rate versus the successfully accessed memory rate. So if we want to do cache optimizations, once again we have seen we can use a larger block size. The block size will be the size of the word. If we use a larger block size and we have way too many requests or orders, that would assist us greatly, as we would always have one space available no matter who we invited and what is going on. A larger total cache capacity to reduce the miss rate. If we have a bigger RAM or cache itself, it will significantly increase the power consumption. We could have a larger total cache capacity to reduce the miss rate. This will increase the heat time and it will also increase the power consumption. We could have higher associativity that would reduce conflict misses and increase the heat time as well as the power consumption. We could have a larger number of cache levels. As we have seen, level 1, level 2, level 3, progressively they get cheaper and bigger. So we could use this higher level of cache, higher number of cache levels. So if we only have level 1, we can add level 2 and level 3, for example, giving priority to read misses over writes. We could have a higher number of cache levels, or we can give priority to read misses over writes. So these are some more optimizations that we could do. Small and simple first level caches would address tag memory. We can compare tag and then select the correct set. Direct map cache can overlap tab comparison and transmission of data. Lower associativity reduces power consumption because fewer cache lines are accessed. Let's look at some properties. This is for the level 1 cache. Size and associativity. Access time versus size and associativity. The dark curve one, the first thing is 1 way, the second one is 2 way, then we have 4 way and 8 way. we can see here the last one, the 8-way, is having the highest values in all categories: 16 kilobyte, 32 kilobyte, 64, 128, or 256 cache size. The same here. We can see the 8-way is having the highest value for the energy consumption in nanoseconds. Another way to reduce the heat time, to improve the heat time, is to predict the way to preset. We could use a prediction to improve the heat time. We would predict the way to preset. So misprediction gives longer heat time. If the prediction accuracy is bigger than 90%, we would use 2-way prediction. If it is bigger than 80%, we would use 4-way prediction. Mirror. Okay, so that is 4-way prediction. We can extend to predict the block as well by using the way selection. Okay, so we have looked at way prediction. Another way to optimize the cache is to improve its bandwidth. This means its speed. So, for example, Pentium will have 1 cycle, Pentium 2 and 3 will have 2 cycles, and Pentium 4 will have the Core i7 with 4 cycles. Level 2 cache must support this, and in general processors can hide the level 1 miss penalty, but not the level 2 miss penalty. Alright, so the non-blocking caches once again would allow hits before previous misses are completed. So level 2 must support this, and in general processors would hide and pretend that we don't know them, but we do know them. That's why hiding from us helps us to remember who we are. Level 1 and level 2, we would give some penalty in terms of the non-blocking sessions or non-blocking caches. we can see here in this visualization the ratio of cache miss penalty. Okay, so that is all that we have today for the computer architecture and memory hierarchies. Alright, so once again we have seen that the memory organization goes in the form of a pyramid. The bigger and the cheaper the storage is, the slower it is. So then the disk and optical disk, accessing those would be slower than accessing the main memory. Accessing the main memory will be slower than accessing the cache, and accessing cache will be slower than accessing the registers, as everybody wants to be in the top of this pyramid in the register. But please be very careful. We have students and coming up for with questions. So once again, the most important, fastest and best memory is the registers, and ideally we would like to have a computer memory that consists only of registers. But because of size and expense, we have this entire pyramid of storages that go into a hierarchy. One goes after the next, contacting each other until they would all eventually read the registers as the CPU needs to execute the instruction set. So that is all that we have today for the memory hierarchy. I guess one more thing is just to remember that those could be turned into a virtual memory, and in that way the programmer or the user does not have to bother or worry about all these different memory hierarchies, but as a virtual machine they take up a common IP address and are able to communicate seamlessly between each other. Okay, thank you everyone for joining us today with our lesson on memory hierarchy.